And
okay, cool.
Ready?
I think it works.
Okay,
yeah.
great. So I'll
Thank you
turn it
so
over
much.
to Caroline.
Hi everyone. My name is Caroline, and I will be talking today about research that I did during an internship with Bloomberg, where I was supervised by Azalea Rath and Julian Van Eyck. For my background, I did a bachelor's degree in mathematics, and I'm right now studying in Amsterdam, so I come from the mathematics side. So the problems that we looked at was exactly as Noam said, termination and divergence. Of course, we would like all of our programs to terminate, but it's quite difficult to show that, and specifically if we actually do have divergent traces, how do we find those? So the approach that all of us probably know is the total logic, where we say, well, we have triples, and our postcondition is a superset of what can happen, and all of our traces terminate. And this is really good if you do this analysis and it works for your program, it goes through, that's amazing, congratulations, you don't have divergence problems. But if it doesn't go through, then you're in a place where you don't know if there's actually divergent traces, or maybe because this is an over-approximating analysis, you actually over-approximated and have a false positive bug report. So the approach that we took to this was, well, we don't want to show that all executions terminate because most likely they don't. So instead we want to show that there exist executions that do not terminate. And this is really, this approach is really dual to total logic in the same way that incorrectness is a dual to our over-approximating logics, because we say, well, we don't want to show the absence of bugs in every case. We want to show that cases exist where those bugs do happen. So the way we do this is through under-approximation. Oh no, it's not. But because incorrectness logic is dual to our normal logics in the same way that our approach is dual to total logics, it makes sense to look at incorrectness logic and see if we can get somewhere, and you are all familiar with the incorrectness triples, I assume. They give us the existence of terminating traces, and they reason in a sort of backwards fashion, and by that I mean is you say, well, for every state in the postcondition, there exists a state in the precondition such that there is a trace through executing C that gets us from pre to post. So by backwards, I mean you first quantify over the post and then you quantify over the pre. This is working really well for a lot of applications. But the problem is if you think about divergence, you don't have a post state to quantify over. You want to say that from a pre state, you can reach divergence. So you sort of need this different direction to get to. So what we do instead is backwards under-approximation. We've heard Flavio talk about this before. They call it the sufficient logic. And this is also what was conceived as the Lisbon triple by Derek Dreyer and Peter Hearn. And this particular version on it is also based on the paper by Azalea Rath, Julian Van Eyck, and Peter Hearn, of which you can find a preprint online. So this triple says, for every state in the precondition, there exists an execution of C that leads to some state in the postcondition. So we say we know about some program behavior and where it leads, but there's a lot of program behavior we don't really care about and we don't really need to characterize. So because we have this different direction that we first quantify over the pre-state and then go to the post, we can very naturally define a divergent version of the triple that looks like this, where you say this triple holds if for every state satisfying the precondition, there exists an execution of C that diverges. And this is really cool, but of course the question is, what does it look like when we use it? So during my internship, I looked at different forms of divergence. We looked at while loops, we looked at recursive functions, but I want to talk about today about goto-soups, because they're quite interesting because they are so unstructured and lead to a lot of chaos. So our setup is that we say a program is a partial finite functions from labels to commands, or you could also envision it as a bunch of blocks of code that are numbered. And goto commands allow us to jump between these bits of codes, and of course, as soon as we have that, we can jump in circles, and we can do that forever, and we have divergence, which is exactly the problem that we would like to take care of. If we execute goto-L, you can see it in the logic rule on the right. It just means that we go to the program block of the same label and execute that block. Now the question is, what are the conditions under which this divergence appears? First of all, it's very straightforward that we have the necessary condition that we have to jump to the same label at least twice. If we don't, we can still have divergence, but then the root cause will not be goto. The root cause will be something else. So we jump to the same label twice, but the problem is we have structures such as assume, so we can change the control flow, and it's possible that even if there's a cyclicity, we go through that cyclicity a number of times, like 3, 4, 5, whatever, but at some point the program still terminates. So it's not enough to say that you jump to the same level twice, because we can still terminate. You need another condition, which is a sufficient condition, and that is that 2 of these jumps occur under the same assumption, and I will get into detail about what I mean by that. But the idea is that at some point we arrive in a place and we look back at the history of our execution, and we say, wait, we've been in the exact same place before. So we have this sort of cycle, and we can find this sort of divergence. So to look at an example, this is a very simple, very stupefied example, where you say you assume that some variable x is positive, you increment it, and then you go to 1, meaning you jump back to the beginning of the line. Now I would like to reason about the fact that go to 1 can diverge if you start with a positive value x. So you say x is positive, we execute go to 1. That means that we execute the program code saved at label 1. This is just a sequence, and we can go through it one by one. We assume it's positive, well, it's still positive, and if we increment the positive x, it is of course still positive. And now we're in the state where we say our assertion is x is positive, and we want to execute go to 1, but we look back into the history of what we've done before, and we've been in this exact place before, so that means we can just go back to the start and execute the same thing again, and we can do that again and again and again ad infinitum, leading to divergence. So this is all very fun, but of course now the question is, how can we actually formalize that in a logic, because we would like to reason about it, of course. The way that we do that is we introduce something we call a conditional triple. This triple is parameterized not only on the program, as all of our triples are, but also on G. And G is a list of labels and assertions. And intuitively, G is the history of what we've seen before. So we say such a triple parameterized on G is valid under the assumptions that if G is a list of things that we've visited before, the triple PC infinity is a valid triple. So we say under the assumption that everything in G we've seen, that G is our history, we know that we have divergence. But of course we would like to connect this to our normal triples, because if you just add on parameters and parameters, it can get very messy very fast. But the way we do that is quite simple, because if you choose G to be an empty list, you say the assumption is that everything in the empty list we've seen before, which holds vacuously true. So the conditional triple parameterized on the empty list is actually equivalent to our normal divergence triple. And now we need rules to reason about it. So what we would like to do is we start with an empty G and we start executing. And upon every goto call, we have the label we call and the assertion we call. And we check if it's in our history, we check if it's in G. And in one case, if it is in G, if we say we've seen it before, we can say, oh, then we have divergence, right? Because we found our cyclicity. But of course, there's the second case as well, where the label and the assertion have not been recorded in our history before. So what we do is we say, well, it's not there, but we have to add it to our history because we go on now, right? And we want to remember that we have passed this point. So we append this to G and then continue executing, which is, the program code saved at label L, because we just did a go to L jump. So to wrap that up, I would like to go through the example we've seen before, but this time we are going to do the proper proof. And the way I do this is I put in red, or looks more like orange, things that we haven't proven yet, and things that we have proven or are trivial are going to appear in green. So we start with a goto 1, and the only rule that we can apply is the goto step rule, because this is an empty list, so our label and our assertion cannot be in the list. So we say, well, it's not in the list, amazing. So we add it to the list. We now have a list of length 1, which has the label 1 and our assertion that x is positive. And we are now executing the program code saved at label 1. This is the sequence, so we go through them. The first 2 bits are quite simple. I have excluded the rules for assume and increment that actually do it because the slides are only so big. But I'm sure you agree with me that these two triples in green hold. And now we're in a place where, again, we're still in the assertion x is positive. It's a very simplified example, indeed. And we, again, want to execute goto1. But now, our list has that label we tried to jump to. And it has that assertion that we're currently in. So this is the point where we say, wait, we've been here before. We don't have to go on. We have found our cycle because we could just do the same thing again and again. So we can apply our goto-rec rule. And we can say we've done. We've just proven that this program has divergent traces. Thank you so much for listening. Please ask questions. Yeah, thank you.
Hey, nice talk, thank you. After the increment on x, you have x greater than 1, that's 0, right?
That is, yes. I mean, if you want to stay exact, yes, but this is not an exact logic, right? Because we have the, because we are in backward over approximation. So what our triples mean is, oh, 1 second. So we say we're starting in the precondition. There exists an execution C that leads to the postcondition, but if we have an execution that leads to the postcondition x is greater 1, we also have traces that lead to the postcondition x is greater 0, right? Because this is as Flavio talked about, we have the forward consequence rule in this logic, so that's why it still holds.
And I have a second question, if you allow me. So you keep the list of locations and predicates, but because you're liberally applying consequence rules sometimes, you could change the predicates in some minute ways.
Yes.
Like your condition is in, it's not like it's implied by one of them.
Exactly, yeah, that's a very good catch, that's true. So instead of saying, instead of saying here that it has to be that assertion, we can say, well, it's included in some assertion.
Or you could apply the rule of consequence.
Or you could apply the rule of consequence before, like you choose that. I kept this representation because I didn't want to muddle the rules even more because I, tried to show the simplest version and then explain it. But you're correct, yeah, that works just as good.
My question is, why goto? Why not something like while or any recursion, anything?
Yes. So while, we can handle while with these goto rules, but we also have a rule to handle while because while is a lot easier, right? It's a lot more structured. So goto is a more interesting case because it's more chaotic. So you have to make more effort to take care of things. We also worked on functions, and in fact, this logic is completely functionally compositional. We can prove terminating and non-terminating specifications. And our functions have local variables, so there's the added difficulty that Andreas talked about in the previous talk, that we sort of have to forget variables and bring them back once we've returned the function and so on. So we've done all of that. I just chose to concentrate on goto because I think that's the most fun case.
So if you go back to slide 24, your definition of your triples.
Oh, wait. I didn't even realize I had slide numbers.
There's no 24. Yeah.
Yes.
Could you redefine the triple as P implies the weakest liberal precondition of false?
I believe so.
Where for WLP you take a maximizing.
Yes, I believe so. This is what Flavio talked about, right?
No, he was under-approximating WP, where WP maximizes.
Wait, sorry, can you restate your question?
So you say P implies WLP of 0.
Weakest precondition of false.
Weakest liberal precondition of false.
What is that? Can you give me the definition of that?
Yeah, so that's all states that either terminate in the post condition or not at all.
All states that either terminate in the post condition.
Or not at all, but we're not saying
But by maximize, you mean you're taking some sort of angelic?
Yeah. For non-determinism, you take angelic.
I'm not sure I can answer the question because I only know half of the words you use.
Yeah, we'll discuss. Later.
Yeah, let's discuss that later, but
Yeah,
I'm very interested
yeah.
in that. But I think Azalea has something to say about that.
I don't think so, because we're not saying this is definitely not terminating at all. We're saying it's possible for some traces not to terminate at all. There you're saying they all terminate or they don't terminate at all.
Yeah, but I'm taking WLP of false, so there's no final state to reach.
Saying there's definitely a trace that doesn't.
Yeah.
Yes. Yes, that's true. Yes.
Yes.
That is what we're saying.
No, it's not.
No.
WLP of false is those states where you terminate on every or you fail to terminate on every execution path. That's what So,
Oh,
but it's related if you have angelic instead of demonic non-determinism. Yeah. It's just like the weakest possible precondition, I think, is WP for angelic. You seem to know that.
there's some doubt there.
This is all related to angelic non-determinism.
Completely different question. So
Yes.
you phrased your logic in terms of programs with gotos in them.
Yes.
If you take a while program, you can compile it down to a goto
Yes.
program. So you should be able to derive similar rules for while
Exactly.
programs.
Yes.
Have you tried that?
Yeah, we have rules for while, and they are very, very simple. So that's why I didn't include them, because if I did, then people would probably be like, well, seen that before. Tell us something new. But yeah, exactly. We have the rules, and they are a lot simpler than goto.
Right. Do you have some completeness result? Like if there is a diverging trace, your logic, you have some derivation in your logic that can find it?
I don't think so yet.
We have two versions of this.
I think you need to speak into the mic.
We have two versions of this logic. One where we only focus on while loops for now. For that we have completeness. This extension that Carolina's worked on handles functional recursion and also gotos. We don't know yet if it's complete, as in we haven't done the work yet, and we don't have an intuition for it yet.
Hi, thanks for the talk. So if I look at the specifications that you have here, and I'm imagining a program with two while loops, the first one terminates, the second one doesn't terminate. I guess I have to prove for the first while loop the first triple, right?
Yeah.
And here you have, it says an execution of C that terminates. So does it mean that for the first while loop I need to prove that it terminates before I can then go to the second while loop to prove that it does not terminate?
You have to prove that it has terminating traces, yes, in the way that the logic is defined. So I think you picked up on the fact that this logic, if you don't look at the divergence, it is total in a way. Because we say, starting from pre, there exists an execution that terminates, and we're not saying there exists an execution that either diverges or terminates. So the answer would be yes. You could, in theory, change the logic a bit, and interestingly, I don't think that it would change a lot about the rules if you were to try to define it as a partial version. The only thing that would change is that functions are easier to deal with because you don't need to prove that functions terminate.
Thank you.
And one more note, because someone asked about functions earlier. I think it was you? Yeah. We can do functions, and it's all like, I mean, it's interesting and it works. But really, we didn't introduce any new ideas for the functions. All of the ideas came from exact separation logic, which is what Andreas talked about earlier. So we just took that proof system and changed it a bit so that it works for our logic.
So, thank you so much for an amazing talk. I have a bit of a naive question, but I was wondering, how do you run into any decidability problems when you're doing something like this, especially once you mentioned some sort of completeness for being able to find the diverging execution?
I'm not sure about that, because again, like, I'm from the mathematical side. I like come up with funny rules, and then I prove soundness, and then I'm very happy because I finished the proof, but I don't actually know if it's useful in real life. So I cannot actually answer that question. I'm sorry.
Anyway, thank you very much.
Okay, sorry.
Is there one more? Okay, let's thank the speaker again.